So in the last class, we discussed lag controllers and started lag lead controllers, and we saw that lag lead controllers. So the last class, this was part one. Part one. Now this is lecture 6, part 2. Lecture 6, part 2. So we saw that lag lead controllers are needed when you have when you want attenuation as well as phase lead, and in that case that means gain attenuation as well as phase lead. Bode plot of the lag lead controller, and this is the transfer function. So their lag part and lead part are connected in cascade. So you can see that their alpha beta equal to 1 and A is greater than B. So as alpha beta equal to 1, so that's why here you can see the magnitude is 20 log beta, and here also 0 dB. So actually, if here the magnitude is 20 log of alpha by beta. So as alpha equal to beta, so that's why 20 it will be 20 here. It will be magnitude will be 20 log of 1. So that's why it is 0 dB. So so because of this alpha equal to 1 by beta, so we are getting a nice plot. Otherwise the plot would have here the magnitude would have been more little bit. But this is not the reason why you are considering alpha beta equal to 1. So the reason, as I said in the last class, is to simplify the design procedure that we will be seeing now. So now the design of lag lead controller. So design of lag lead controller. So in the last class also we saw that why the lag part will come first and then lead part, because we want gain attenuation as well as phase lag together. Sorry, gain attenuation and phase lead. Gain attenuation and phase lead. So for practical system, this may be needed when we want to trade off the performance obtainable by lag and lead controllers. That means using lag controller, what will happen? The system can meet phase margin, but gain cost of frequency will reduce very much. On the other hand, with lead controller system can satisfy phase margin, but their gain cost of frequency will increase very much. That means it will become fast. That means it will become fast means more noise it can enter into the system. It may be noise prone. Now to trade off between the two, that means to obtain a gain cost of frequency in between, we will use lag lead controller. So now the design, the same algebraic method of design we will be using as we have used for lag and lead controller. So what is the objective? So objective is given a phase lead of phi c and attenuation phase lead of phi c and attenuation MC in dV. MC is negative, remember that here. But here phase lead, that means phi c is here positive. So at a particular frequency omega c, determine the controller parameter. What are the controller parameters? A, B, alpha. Because once alpha is known, then beta will be equal to 1 by alpha, because alpha beta equal to 1. So in this way, we have reduced this alpha beta 2 parameters to 1 parameter. So if alpha not equal to beta, then the design will be complicated. Now we will be seeing those things. Now solution. Now what is the solution? So what is the gain attenuation? If you see this figure, so what is the gain attenuation provided by the, so this frequency range we will be using, as I said, this operating region. So in this operating region, you can see, so what is the gain attenuation provided by the lag part, that will be 20 log beta. Is 20 log beta. What is the is 20 log beta? What is the gain? What is the gain amplification provided by the lead part? Lead part is suppose the frequency is at here omega c. So according so as per the equations of lead part, and we will get what is MC. So here MC will be equal to 20 log beta. This is the gain attenuation provided by the lag part plus the gain provided by the lead part. But ultimately this sum should be negative, because so that means beta should be greater than that means beta is less than 1. Beta is less than 1, but ultimately this sum should be such that MC is negative in dB. So this is 20 log of alpha into root under omega c square plus s square divided by root under omega c square plus alpha square s square. So this is the gain at this, I said, attenuation by the lag part. This is attenuation by the lag part, and this is gain by the lead part. Gain by the lead part. So ultimate some attenuation we will want. That means this part will be more negative than this part should be. This part should be more negative than this. That means so that ultimately MC is negative. 20 log beta. 20 log beta should be less than this one, such that MC is negative. So this you can write like that this, from this MC by 10 you will get MC by 10 equal to log of beta square 10 base. All these are base 10 that I am not writing. Beta square plus log of, you can write, so it will be 2 log alpha into this one. So 2 if you want to absorb here, it will be square. So it will be alpha square into omega c square plus s square divided by omega c square plus alpha square a square. So this will imply mc by 10 equal to log of, so alpha square beta square. So if you want to absorb this one inside, alpha square beta, so alpha square beta square is ultimately 1. So this will be omega c square plus a square divided by omega c square plus alpha square a square. Now omega c by a, I have already assumed earlier in case of lead part, lag part, omega c by a is the normalized omega c. That I had denoted as omega c bar. So the same notation I will follow. So this is equal to log of omega c bar square plus 1 divided by omega c bar square plus alpha square. Here again I am writing omega c bar equal to omega c by a. Okay. So from here, then I have also defined that C. Then C I have defined earlier in case of lag, lead, all the controllers 10 to the power of mc by 10. Here mc is negative, mc attenuation means negative. So this will be equal to, from this equation, it will be just omega c bar square plus 1 divided by omega c bar square plus alpha square. Okay. So this is about your C. Now what is your Q? So earlier Q was tan phi C. So Q, now Q, here Q, in here Q, or in, I'll write, okay. So here Q equal to, so tan of, so now phi C is the amount of gain attenuation I needed. But unfortunately, I have to, because of the lag part, this sorry, phi C is the amount of phase lead I need. So but because of this presence of lag part, it will provide some amount of, very small amount of phase lag also. That means ultimately I have to provide little bit more phase lead, so as to compensate the phase lag provided by the small phase lag, say 2 to 5 degree phase lag, or 1 to 5 degree provided by the lag compensator. Because we'll be, as it is shown in this figure, we'll be operating in this region. Okay, in this region it may happen, the if B and A are far away, then the lag part will not contribute any phase lag. But if B and A are not too far away, then whatever phase lag we are expected with lead part only, but some amount of that phase, some amount of negative phase will be provided by the lag part also, because at that time lag part phase will not become zero. Okay, so that's why a little bit of phase, additional phase we have to provide, so as to nullify the phase lag contributed by the phase lag given by the lag part. So this is the, so this is the small phase lag, small phase lag by the lag controller. So that's why I want actually phase lead of phi C, but I have to calculate for more, so as to nullify the additional phase lag provided by the lag controller. So lag controller additional phase lag. So here 1 degree to approximately 5 degree, because that is those frequency. This range is actually away from this small part, so away from B. So phase lag will be very small, but still you cannot neglect totally. So we have to consider in between 1 to 2 degree, and then calculations we have to make. Amen. Okay, so now Q is tan of phi c. So this is the phase lead to be provided. This is the phase lead. This is the phase lead. Phase lead to be provided by the lead part. Lead part. Okay, so this is the phase lead to be provided by the lead part. Okay, okay, this much I'll remove. So now, so from here, what you will get from here, now this Q is what? So we know what is Q, because ultimately phase lead will be provided by the lead controller. So the expression of Q will be same. So here I should write now Q equal to what? Q equal to the expression. The expression will remain same. So this was in case of Q. What was the expression of Q? Omega c bar into alpha minus 1 divided by alpha square plus omega c bar square. So this will be now same as lead controller, because ultimately this Q has to be provided by the lead controller. Okay, so that's why this Q expression will remain same. So now, so from 1 and 2, from 1 and 2, from 1 and 2, by eliminating omega c bar, one obtains same elimination, same method. That means what you have to do, you have to take just omega c, you have to find from here. Okay, and then once omega c you get, you have to substitute here omega c square to substitute omega c square. What you have to do, you have to square up the both sides, and then you can substitute. Then ultimately you will get an equation involving q, c, and alpha. So ultimate equation same as we have obtained in equation 5 of lead controller. Similar kind of equation we will get. So from 1 and 2, by eliminating one obtains. So this equation we will get. I am not deriving this one here. You can easily check. Please, I suggest you to please derive it. The same process as we have followed for lead controller. So this alpha square plus 2q square c alpha plus q square minus c plus 1. This is equal to 0. So now what you have to do? Now we have to see what is the condition. What is the condition for existence of solution? So here also, what is alpha? Alpha is greater than 1. Alpha is greater than 1. So positive solution. So here also, as similar to the lead controller, as q square c greater than 0, for existence of a positive solution, what is the condition for existence of positive solution? So you can compare this equation like, as I said earlier, ax square plus bx plus c equal to 0. So if you want to have a positive root of x, at least one positive root of x, then you have to have a into c should be less than 0. So a into c should be less than 0, but what about c here? So a into c should be less than 0. So for existence of a positive solution, q square c plus c minus 1 into q square minus c plus 1 should be less than 0. So this will imply ultimately what? So now since c is less than 1, because c is ultimately attenuation, MC is attenuation, MC is negative, so C equal to MC by 10, so it will be negative. So this implies Q square, since C less than 1, Q square minus C plus 1 will be less than 0. Therefore, so here another C will be there. So this is less than 0. So this into C will be less than 0. Okay, C is greater than 0, but C is greater than 0. C is greater than 0, but this term is no, this C is greater than 0, and so 1 minus C is greater than 0. 1 minus C is greater than 0, so this should be greater than 0. This should be greater than 0. This should be greater than 0. So therefore this term should be less than 0. So q square c plus c, q square c plus c minus 1 should be less than 0. So this will imply c should be less than 1 by q square plus 1. So you can, similar to the lead controller, you can also show that the existence of a positive solution will suffice to ensure that the alpha is also greater than 1. So that the same way you can just show. So that means this is the necessary and sufficient condition for existence of, so necessary and sufficient condition for existence of lagged lead controller, because alpha, once alpha you can get, beta you can get, then for computation of b will left b and a. If b and a you can easily compute, so that way I will show. So this is necessary and sufficient condition for existence of lagged lead controller. So as I said, I am just writing note, a positive solution of alpha ensures alpha greater than 1 as well, as shown in lead controller case. So again I am not saying that. Okay, so this you can easily prove. So just before equation 5 of lead controller, as we have shown, similarly here also you can easily show that this if that from here if one positive solution exists, from here you can in fact prove that if a positive solution exists, then that solution will be greater than 1. Okay, so well, so now suppose alpha solution you have got from this one, then what will be your a? So once alpha is obtained, then a will be what? So now one thing you see, that from this equation, yeah, so this equation mc by 10 q so where is omega c bar? Omega c bar we have assumed as omega c by a. So what is the relation between c and this one? From here you just see omega c square. Omega c square will be equal to what? Omega c square, you can get omega c square, if you take, it will be just 1 minus c. Omega c square will be what? 1 minus C divided by alpha square C minus 1. So from 1, then from 1, A will be equal to, so from 1, from 1, C omega bar square plus C bar alpha square, C into omega C bar square plus C into alpha square. This is equal to C into omega C bar square plus C alpha square equal to omega C bar square plus 1. Omega C bar square plus 1. Omega C bar square plus 1. Yeah, omega C bar square plus 1. So from here, what will you get? So here you are getting, so omega c square bar square into 1 minus c. So this is equal to what? Alpha square c minus 1. So this will give you omega c bar. This is equal to root under alpha square c minus 1 divided by 1 minus c. So this will give you omega c bar is what? Omega c by a. So this is equal to root under alpha square c minus 1 divided by 1 minus c. From here, you can get what is your a. A will be omega c into root under 1 minus c divided by alpha square c minus 1. So that means once you solve, once you get alpha by solving that second order equation, this equation, your second order this equation, then you can obtain this A. That means lead part. So once A you get, so the parameters of the lead part alpha and A you can find out like this. Now about lag part. So B as alpha beta equal to 1, so beta will be directly you can find 1 by alpha. Now what is your B? So to calculate B, to find B, this is to find B. If what is known now, if alpha is known, so that means first lead part you have to find out, then lag part B, lag part corner frequency B you can find out. So once B is once alpha is known, now what is phi 2? Phi 2 is the phase lag provided by the lag part. So you can easily write then tan of minus phi 2, that is the, so phi 2 equal to tan inverse of what? Omega c by b minus, so I'll write in that way. So phi 2, what is your phi 2? So phi 2 is your tan inverse of, phi 2 is what? Tan inverse of, what is your lag part? Lag part transfer function is this one, tan inverse of omega c by b minus omega c by beta b. So tan inverse of omega c by b minus tan inverse of omega c by beta b. So what is phi 2? Note phi 2 negative. So phi 2 is actually negative. So actually minus phi 2 equal to, minus phi 2 equal to, this is the negative phase. So phi 2, this is the phase, this phi 2 is negative. So that so that's why I have written minus phi 2. So that means tan of, this means tan minus tan phi 2 or tan of minus phi 2. So this you will get as omega c by b minus omega c by beta b divided by 1 plus omega c by b into omega c by beta b. So from here, what you can write? From here, you can write tan of minus phi 2. This is equal to omega c by b. So now 1 by beta equal to what? 1 by beta equal to alpha. So omega c by b into 1 minus alpha divided by 1 plus omega c by b. 1 by b is again alpha. So that means this square into alpha. Okay. So from this equation, you can now write, if you divide the numerator, no, if you multiply by numerator and denominator by b square by omega c square, then you will get this kind of equation: b by omega c square plus alpha. Please check it: alpha minus 1 into tan of minus phi 2 into b by omega c plus alpha. This is equal to 0. Okay, here alpha, remember, that is greater than 1. So now omega c, so you have to solve for b. So we will assume, one can assume that omega c is much greater than b. In fact, it is greater than b, much greater than b. Otherwise, that phase lag, considerable phase lag will be provided by the lead, and we are assuming that the phase lag provided by the lag controller is negligible, almost 1 to 5 degree. So that's why that omega c is much greater than b. That means b is much smaller than omega c. Also, b is real, of course. B is positive, real, positive solution. So from here, what you have to do? Take the smaller of two real positive solution. So alpha is greater than 0. Alpha is greater than 0. So also this is your minus. So here smaller two real solution you will get. So here two real solution you will get. This is phi 2 is, this is negative, and here alpha is greater than 0. So take the smaller of two real positive solution, since to obtain b. Why? Because since b is much smaller than omega c. Because as I said, if you do not consider this one, then the phase lag part may contribute some more phase lag. So here phi 2, then in that case phi 2 equal to 1 to 5 degree, that will not suffice. So more phase lead has to be provided by the lead part to compensate for the lag provided by the lag part. Okay. So this is so that means there are 3 steps. So this is the last one. So first step is that you have been given, the design procedure is like this. You have been given a phase lead phi c and attenuation MCDB at some frequency omega c. You have to determine A, B, alpha and beta. Beta equal to 1 by alpha. So that's why A, B and alpha is okay. So what you have to do first? You have to solve first this equation. Solve first this equation. You have to solve first this quadratic equation. Solve first this quadratic equation. This quadratic equation you have to solve first. So if you solve this quadratic equation, then you will get alpha, and but before solving this one, you have to check whether lag lead controller is exist or not by checking this condition. So then once this condition is satisfied, then you have to solve this equation for alpha, and then you have to so once the solution of alpha you will get, then the parameter a will get from this equation, and then and then finally the parameter b of the lag part you will get from this one, and the beta you will set as beta equal to 1 by alpha. So then the controller design will be over. Okay, sorry, lag lead part design will be over. So now one example we will consider. So determine the transfer function of a lag lead controller that will provide a phase lead of 50 degree and attenuation of 15 dB at omega c equal to 6 radian per second. So consider phi 2 equal to 2 degrees. So that is given. Phi 2 equal to 2 degrees. So just so this example is just to illustrate the design process. Just to solve these equations and design the controller. But actual if a plant transfer function is given and some specification is given, whether lag part is required or whether lead part is required or whether lag lead controller is required. So all these things solving will be giving in the next class. Okay, we'll be studying all the things in the next class, but now we'll solve only this lag lead controller, and here phase lead is how much phase lead is needed, that is given. How much attenuation has to be given, that is also given. But in actual problem, phase lead, this much phase lead is given, this much attenuation is given is needed, so that will not be given. We have to find, depending on our requirement, how much phase lead is required and how much attenuation is required. So solution of this problem for the timing will do. So here what is q? Q is here. So tan of how much phase lead is needed, 50 degree, and how much lag controller, how much lag the lag controller will provide is 2 degree at this frequency omega c. So this if you compute, this will be equal to 1.28 degree. Okay, sorry, 28. 1.28. So then what is your C? C will be equal to 10 to the power mc by 10. So mc by 10. So that is equal to 10 to the mc is what? Minus 15 by 10. So this is equal to 0.0316. Now you can easily verify that your C is less than 1 by q square plus 1. You can easily verify 1 by q. Note C is less than 1 by q square plus 1. You can easily, it is satisfying. you can easily check. So this implies what? Lag lead controller can be designed. Lag lead controller can be designed. Okay, so lag lead controller can be designed. So now the parameters. What are the parameters we will compute? So first, as I said, we will be solving the quadratic equation. So the quadratic equation becomes, so first part will be to solve alpha and a. Okay, so to solve alpha and a, so the quadratic equation becomes q square c plus c minus 1 into c alpha square plus 2q square c into alpha plus q square minus c plus 1. This is equal to 0. So this if you put all those values, then it will be all the values of c and q as shown above. Then it will come out to be like this, minus 0.0282898. Please check all these calculations. As I said before also, 0.1036 alpha plus 2.6066, this is equal to 0. So this will give you ultimately alpha equal to 11.4376. Okay, this is about your alpha. And then what is your a? Then a will become just omega c into root under 1 minus c divided by alpha square c minus 1. If you put all these values, then you will get like this: a is equal to 3.3337. So that means lead part design is over. Then beta will be equal to your just 1 by alpha. That I am not writing, just to solve. So now which one is left to solve for? To solve for b. So only b part is left. To solve alpha and a, to solve for b. So how will you solve? So b, as you know, b by omega c, b by omega c, whole square, this equation, plus alpha minus 1 divided by tan of minus phi 2 into b by omega c plus alpha, this is equal to 0. So lead lag controller design is little bit involved because it is little bit lengthy, as you can see now. So this is b by omega c square. So if you compute, so this will be just b by omega c square. This will be minus 298.893 into b by omega c plus this will be 11.4376. This is equal to 0. So this will give you b by omega c equal to 0.0383. So this will give you b equal to 0.2296. So here, as I said, the smaller value of b by omega c you have to take. There will be two solutions, but the smaller value you have to take because b is much less than omega c. You have to assume. If you do not assume, then the phi 2, that is the phase lag, unexpected phase lag that is provided by the lag controller will be more, and that you have to compensate. That means phase lead to nullify that phase lead part has to provide much more phase lead, which is not desired, which is not means acceptable. Okay, so this is your B. And then ultimately, then the lag lead controller will become, then the lag lead controller becomes HS will be equal to S plus A into S plus B divided by S plus alpha A into S plus beta B. So this is will be equal to S plus 3.3337 into S plus 0.2296 divided by S plus alpha into A. It will be 38 point. Please check all these calculations into S plus 0.0201. Okay. So you can see that lag controller is acting like almost pure integrator into PI type of controller here. Because the lag controller, the main objective here is to provide phase attenuation. And the phase lag that is provided by the lag controller is assumed to be negligible. There's only 2 dB here. So now, how to realize a lag lead controller? So that part we will now see lag lead controller implementation. I will go to next page. Well, here also we can do so lag lead controller implementation. And the circuit that we will be using is this one. Okay, so better to go on in the next page. Go to the next page. Next page we will go. So this is your capacitance. This is your V2 and this is your V1S. V1. Okay. This is your R1, C1. This is R2. This is your C2. So if you get just we want to show that whether this condition we want to just see that whether this circuit represents the transfer function of a lag lead controller. That means V2S by V1S is a transfer function of a lag lead controller. So V2S by V1S is what? So here you can easily see that what is, suppose your current is I here. What is your I? Here IS will be equal to V1 divided by R1 parallel 1 by C1S plus R2 plus 1 by C2S. Then from here, what is your V2S? V2S equal to R2 plus 1 by C2S into I. So this will imply V2S by V1S will be equal to R2 plus 1 by C2S divided by R1 plus 1 by C1S plus R2 plus 1 by C2S. So this, sorry, this is parallel. So this can be written as V2S by V1S. This is equal to what? This will be your R2 plus 1 by C2S into R1 plus 1 by C1S. Please check it. Your R1 into 1 by C1S plus R2 plus 1 by C2S into R1 plus 1 by C1S. So if you go ahead, then it will look like it will be R2 plus 1 by C2S into R1 plus 1 by C1S divided by this will be this will be 1 by R1 R2 plus R1 by C1S plus R2 by C1S plus R1 by C2S plus 1 by C1 C2 S square. So this can be further simplified to like this: V2S by V1S, further simplified like that. Please check it. It will be C1. It will be so if you take R1 R2 common from this one numerator as well as denominator, and then it will be just 1 plus 1 by R2 C2S into 1 plus 1 by R1 C1S divided by 1 plus 1 by 1 plus 1 by 1 by C1 R2 S plus 1 by C1 R1 S plus 1 by C2 R2 R2S plus here actually this will continue 1 by C1 C2 R1 R2 1 by S square. So this can be further simplified. So if you multiply in the numerator as well as denominator by S square, so it will come out to be like this. So this will be S plus 1 by R1 C1 into S plus 1 by R2 C2 divided by this one S square plus S into 1 by C1 R1 plus 1 by C2 R2 plus 1 by C1 R2 plus 1 by C1 C2 R1 R2. So here plus means here actually. Okay, not additionally. Means with this C1 1 plus 1 divided by C1 C2 R1 R2 is a part of the denominator polynomial. So this means V2 by V1. If you want to write like this, equal to, if you write s plus a into s plus b divided by s plus alpha a into s plus beta b, because alpha beta equal to 1. So then where a is what? 1 by c1 r1. What is your b? B is 1 by c2 r2. What is your alpha beta? Alpha beta is 1, so alpha beta into AB should be equal to 1 by C1 C2 R1 R2. So A alpha beta equal to 1. So A into B is C1 R1 C2 R2 is satisfying. That is fine. Then 1 by then alpha A plus beta B. Alpha A plus beta B should be what? Alpha A plus beta B should be equal to this. Alpha A plus beta B. This should be 1 by C1 R1 plus 1 by C2 R2 plus 1 by C1 R2. Okay. So now if you see 1 by C1 R1 plus C2 B2 is what? Alpha A plus beta B. This is equal to A plus B plus 1 by C1 R2. So only your 1 by C1 R2 has to be like this. Alpha minus 1 into A plus beta minus 1 into B. So this has to be satisfied, this condition. So C1 R1 C2 R2 has to be chosen such that this condition will satisfy. That means C1 R1 equal to A, C1 R1 equal to 1 by A, C2 R2 equal to 1 by B, and then C1 R2 has to be like this, alpha minus 1 into A plus beta minus. So suppose given A, B and alpha, if you want to realize like this, then C1 R1 should be 1 by A, C2 R2 should be 1 by B, and 1 by C2 R2 should satisfy this equation. Okay, so another thing is that, so note, no amplifier is needed also. So here no amplifier, like unlike lead controller, no feedback amplifier required. No feedback amplifier is needed. Okay, no feedback amplifier is needed. So so I will wind up now. After this 2 days after this class, so next class I will continue. So in the next class I will consider one example where only specification of steady state performance and steady state error tolerance and phase margin and gain coefficient frequency is given, and we have to design lag lead or lag lead controller, and we have to, in fact, we will not be given what is the gain coefficient frequency. Only some frequency response data will be given. We have to find what is the gain coefficient frequency. We need to design lag controller. What is the gain coefficient frequency needed to design the lead controller and lag lead controller. So this is that will be a complete design problem. So in the next class that we'll see. Okay. So just I will go through once again overall if there is any mistake. If there is any minor mistake, that I will let you know in the next class. So if there is a major mistake, then I have to again record this class. I think there is no major mistake. All the things are major mistake is in the mistake in the derivation. Plasma mistake I can I can rectify in the PDF copy. I think it is fine. So lead controller, as I said, lead controller is needed. So all controller design here, lag lead controller design objective is same. That means three specifications we have to meet. One is steady state error requirement, and steady state error specification, phase margin, and some gain coefficient frequency. So where steady state requirement will be met by the servo gain part, that is K, and the phase margin and gain coefficient frequency part will be met by the normalized controller part. So lag lead part. So using lag lead or lag lead and lag lead. So phase margin part can be met. But if you want to design, if you want to make omega c fast, that means if you want to make fast, that means higher omega c, then you have to use lead. If you want to use much slow system, slow omega c, slow gain coefficient frequency, less gain coefficient frequency, then you can use lag. And if you want to trade off, if you want to get a gain coefficient frequency in between, then you have to use lag lead. So that is the philosophy. So lead controller will provide phase lead as well as gain amplification. Lag controller main objective is to provide gain attenuation. Of course, little bit of phase lag will also provide in this process. And lag lead controller, the objective is to provide gain attenuation and phase lead together. So that is a contradictory objective we will meet using lag lead controller. Okay. Thank you.